Let us just summarize the results of stage 1. So, in the carry lookahead adder of this stage, we compute the generate and propagate the GP functions for increasing sizes of blocks in a tree-like fashion. So, going to the previous slide, we initially do it for small blocks of 2-bit pairs, 4-bit pairs, 8, 16, and 32. So assuming that there are n bits that we want to add, there are a total of approximately log n levels, log n to the base 2. The time per level is O1, which means it's constant time. And the reason that it is constant time is because we don't have to do a lot of work to compute GNP functions. An AND gate in one case and or an AND gate in another case. So total time for stage 1 is order of log n. So that's for stage 1. So we have not done the addition yet, but let's take a look at how the addition would be realized. Let us now look at stage 2 in all its detail. So recall that this is exactly the same diagram that we have been looking at earlier also for stage 1. There are a couple of changes, so I'll discuss that. So in stage 1, the aim was different. The aim was to compute the generate and propagate functions for level by level. So we pretty much, so if you would recall the diagram in stage 1, we started out with 2-bit blocks. So basically the reason we did that is that an equation for a generate and propagate function for a 2-bit block or a 2-bit system is not that complicated. So we started out with that, reduces the number of levels. And then we just created a tree of GP blocks and aggregated this information till we went to the top. So a total of 6 levels actually from 0 to 5. So we have the same diagram here, it's just we have added some more interconnections for stage 2. So in stage 2, the idea is that once we know the generate and propagate function for each block, we should be able to efficiently compute the carry. And once we know the carry, we can quickly do the addition. So since we have considered 2-bit blocks, the first change that we do is in level 0. So what we do is that we consider this group of 2 bits, right? 2-bit pairs actually. So since we're adding 32 bits, there'll be 16 2-bit pairs. Each one of them can be added with a 2-bit. RC is a ripple carry adder. But the main thing that stops us from doing the addition is that we don't know what's the carry. For example, for this 29th and 30th bit pair, we don't know what is the carry that is coming inside. Or we don't know that what is the carry coming inside the 31st or 32nd adder. If we know that, if we know all the carries that are coming into these adders, we can quickly in order one time do the addition. So the idea is to quickly compute all the carries such that we can use the ripple carry adders here to do the addition and then compute the result bits. So result bits, if you're adding to 32-bit numbers, there can be a 33-bit result. So we're not showing the additional bit just to keep the diagram simple, but that needs to be kept in mind. Alright, so to quickly compute the carry, let us view a GP block slightly differently. So each GP block has a range of bits. For example, this GP block over here is considering the range of bits from the 17th position to the 20th position. So we are calling it R1 and R2. And so this is like from 29 to 30th. So the range is set. For each of them, if we get the carry in, we can always compute the carry out with the simple equation, which is carry out is the generate value ORed with the propagate value and C in, right? So this is a very simple thing. This requires one OR gate here and one AND gate. It's a constant time per block. But the aim is to quickly compute all the carries. And that's what we shall try to do now. So let's do one thing. So there are a lot of wires actually over and above the wires that are shown here, but not all of them are being shown. I've just showed a couple for the purposes of illustration. So let's consider two 32-bit numbers that we are adding. So in this case, there is no carry in, but let's consider a general case. where there can be a carry in into the first bit. So what we do is that we take all the rightmost GP blocks, rightmost when we are looking at the screen. So at t equal to 0, we essentially connect all the carry in the Cn values to the rightmost GP blocks. So the ranges are 1 to 2, 1 to 4, 1 to 8, 1 to 16 and 1 to 32. So let us assume for the purpose of explanation that the time it requires to the time it requires for one GP block to compute C out, which is same for all the blocks shown over here, is one time unit. So to compute C out, it is one time unit. Alright, so it takes one time unit to compute C out. And so similarly, we need to find out how many time units it takes for to do the entire addition. So our main aim is that for each of these 2-bit adders that we have shown here, we need to find all the carries. If we can do that very quickly, we are all done. So let's again consider the beginning of stage 2 when t is 0. We connect all the C input, so the carry in values, I'm sorry. And so then after one time unit, essentially all of these GP blocks are ready with their carry out. So we know the carry out after the second bit pair, after the fourth bit pair, 8, 16th and 32. So we can again, draw one more front. So this front is when t equal to 1. So everything to the left of it, we don't know the carries, but to the right of it, we know all the carries that are there, or all the carry outs we know. So now let us do one thing. Let us look at how do we interconnect these blocks. So let's take a look at one example. And then the rest of the blocks are also connected in the same way. So we don't have to take a look at everything with too many wires. So let us consider this block, which after t equal to 1 has its carry out ready. This ranges from 1 to 16. So for this particular block, since we know the carry out after the 16th bit pair, it can be connected to all the other GP blocks which start from the 17th bit pair. For example, this one, this one, this one and this one. So at t equal to 1, when the carry out of this block is available, it can immediately be sent to the rest of the blocks, these 4 blocks. And then at t equal to 2, the carry out at the end of these blocks would be there. For example, at t equal to 2, we'll find that this GP block would be ready with a carry out of the 24th bit pair. So let's again erase the ink. So we'll realize that at this point at t equal to 2, right? So basically at t equal to 0, we are here, right? At pretty much at the very beginning. At t equal to 1, we know the carry out at this point. And similarly for other points, I'm just showing one particular path. Then at t equal to 2, we are at this point where we know the carry out of the 24th bit pair. So this GP block is connected to all the other blocks which so always we will connect something at a higher which is sort of higher on the screen and whose level is lower. So that's the way that we'll proceed. So in this case, we will connect this with this block, and so there can be other blocks also, but let me just show one. So in this case, we'll connect it with this block. So this is the range is 25 to 28, and so since this block here produces a carry out at the 24th bit position, we should be able to connect it. So basically, at t equal to 2, it will get the value of its carry in. Then at t equal to 3, we will get, so this block will finish its computation. We'll get the carry in at this point for the blocks which looks at the range 29 to 30. Then at t equal to 4, this block will finish its work. This block will finish its work. So the input again to this adder, so the carry in will be available because this block would have computed its carry out. So this is 29 to 30, so the carry in at the 31st position would be ready. So in a similar manner, let me again erase all the ink on this slide. So basically, what's the idea? The idea is that we start at the beginning with the rightmost blocks, and at each stage, we send the computed carry out to one of the blocks at lower levels. So at t equal to 0, we are here, then at t equal to 1, we are here. So the front keeps on advancing, and all the blocks at the lower levels sort of keep on computing their carry. So basically within 4 steps, we were able to compute the carry out here. I'm sorry, the carry in at this point. So this holds true for all the other points as well, that within a maximum of 5 steps, the values of the carry input values of all of these adders would be there. So let's maybe consider the example with bit pairs 17 and 18. So let's see how its carry in will reach it. So let's take a look at 17 and 18. So t equal to 0, we are over here. At t equal to 1, we have computed the carry out over here. And this immediately reaches the ripple carry adder, which is adding the bit pairs 17 and 18 at t equal to 1, and an addition can be done. So let's maybe look at 23 and 24, right? Let's look at the bit pairs 23 and 24. So essentially the way that things would pass is something like this, that first, so I'll show the sequence of GP blocks, their ranges. So first we'll go from 1 to 16. So this is, the carry in is flowing this way. So at t equal to 0, we are here. At t equal to 1, we'll be here. This will be connected to a block whose range is between 17 to 20, right? So at t equal to 2, we will have the carry out value over here. This will again be connected to one more block whose range is 21 to 22. So the end of t equal to 3, we will have the carry in over here, and finally this will be connected to the block whose range is 23 to 24. So basically by t equal to 3, the carry in here will be available, and we can then perform the addition. So we can convince ourselves that for each of these blocks at the end of 5 steps, we are guaranteed to have the carry in available for each of these adders, and then we can perform the addition, which is a quick step. It takes a constant amount of time, right? So keeping this in mind, let me once again explain this in a textual way. See, each GP block represents a range of bits R2, R1 to R2, where R2 is greater than R1. So the R2, R1 GP block is connected to all the blocks of the form R3, R2 plus 1. And to avoid extra connections, we can assume that these blocks are at a lower level. So the carry out of one block is an input to all the blocks that it is connected with. And each block is connected to another block either at the same level or at lower levels, as we discussed. Sometimes same level connections are also not necessary. So we clearly want to minimize the number of wires. So we start at well, it should not be the leftmost blocks in each level. Sorry, it should be the rightmost. Well, it depends on how you are looking at it. It depends on how we are looking at it. But if we are staring at the screen, it should be the rightmost blocks actually, not the leftmost. And then we feed it an input carry of C in 1. So then each block will compute the output carry and send it to all the blocks it's connected to till it reaches the ripple carry adders. And so basically this is again the same diagram shown once again just to reinforce the facts of how this is done. And then let's move to 44 slide. So in this slide, let's take a look at the time complexity. So the time complexity is that it's the time taken for a carry to propagate from one node to all the other nodes. And since we go down one level in each time unit, uh, it has its limit. It has order of log n steps. So basically, stage one took order of log n steps. Stage two takes order of log n steps, and addition at the end is constant time, so we ignore. So here we go. The total time that it takes is order of log n, which is exactly what we had set out to prove. That we can have an adder, in fact a very fast adder, and this adder is also used in commercial circuits, and it takes order of log n time to finish its computation. So let us summarize the time complexities of different adders. The ripple carry adder takes order of n time. The carry select adder that we discussed. So what was the idea of the ripple carry adder once again? The idea of the ripple carry adder was that we basically have these fixed size blocks, and maybe with 1 bit pair or 2 bit pairs, doesn't matter, and then we do the addition and the carry sort of ripples. So that's the reason in a worst case it can take order of n time. What we did with the carry select adder is that we had slightly larger blocks, but in the first stage we actually computed two results, one with an input carry of 0, one with an input carry of 1. So we had two results. And so then what we did is that we quickly took a look at, so let me maybe clean this up slightly such that I can re-explain in a better way. So what we did is that we computed two results, one is an input carry and input carry assuming 0 and one assuming 1. So given the value of the input carry at the beginning, we were quickly able to compute the output carry maybe this way and choose a set of results uh, based on the carry out. So we figured out, we got an equation of the form order of k plus n by k, and so this we differentiated. So and then after some calculus, the time came to order of square root of n. So carry lookahead adder is our latest adder in our portfolio of adders. It's very fast, it's the fastest. It is also used in commercial processors. So this takes order of log n time, and log n is clearly much faster than order of n or square root of n. So the advantage here is that it's again a two-stage algorithm, which is very fast. That's the advantage. And the way we do it is basically via creating a tree that computes the GP functions. So you first walk downwards, compute the GP function for each block, and then we walk upwards where we compute the carry outs for each bit pairs, and finally we use a ripple carry adder to do the addition. Okay, so we shall take a look at algorithms for fast multiplication next. So let us go back to class 2 and take a look at how multiplication is done, and then once we figure out how multiplication is done, we'll make a computer circuit for it. So let's try to multiply 13 times 9. So 13 times 9 in base 10 is 117. So this is in base 10. So let's now try to multiply 13 times 9 in binary. Let's consider them unsigned binary numbers. So 13 is 1101, 8 plus 4 12 plus 1 13, and 9 is 1001. So the way we perform multiplication in binary, we shall see, is exactly the same as the way we do multiplication in decimal. There's no reason why it should be different. So before looking at the multiplication, let's define some terminology. So the number that we write on top, it's a matter of tradition, is called the multiplicand, and the number that we are writing at the bottom, which in this case is 9, is called the multiplier. So of course the multiplicand and multiplier are symmetric terms, but one of the numbers has to be in our system. One of the numbers which is written at the top Let's just call it the multiplicand, and the one that's written at the bottom. So in this case, 13 is written at the top, so that's the multiplicand, and 9 is the multiplier, and 117 is the product. So in this case, 1101, which is the binary representation of 13, is the multiplicand, and 9 is the multiplier. So let's do one thing. So what do we do while multiplying base 10 numbers? Is that we start from the right and move towards the left. For each digit, we multiply the multiplicand at the top with the digit. So let's first consider the first digit here, the rightmost. So this is 1, so we multiply the entire multiplicand by 1, so we get 1101. Fine, then we move to the next digit, which is 0. So 0 times any number is 0, so we just write 4 zeros below the other, 0, 0, 0, 0. Next, in the next digit, we again have a 0, so we write 4 zeros once again, 0, 0, 0, and 0. And finally, we come to the leftmost digit, or the MSB digit. So since we are looking at unsigned numbers, we are relatively safe for now, and this is not the signed bit. So we multiply again 1101 times 1, so where the result of that multiplication is 1101. So now what we need to do is that uh, so each of these numbers that we computed is called a partial sum, right? So 1101 is a partial. So each of these, roundish, bluish, rectangular boxes are known as partial sums. So we need to add up these partial sums. And mind you, the one partial sum is offset by one position to the left as compared to the previous partial sum. In a sense, it's multiplied by 2. So what we do is that we take 1. So 1 is essentially added with 0. So we can write a 0, So just to make the addition easier to visualize, we can write zeros here. So this is exactly the same as the normal base 10 multiplication that little children learn when they are in the second grade or third grade or fourth grade. So what we do is that we add 1 with 0, so we get 1. At this point we get 0. We add 1 with 3 zeros, so we again get a 1. And 1 plus 1, we use it to get a 0. And there's a carry of 1. So 1 plus 0 becomes 1. Then 0 plus 1 is 1. And again we have 1 here, so this is what we have. So what is this number? So this is 1 plus 4 plus 16 plus 32 plus 64. So this number is, so if we add 64 plus 32 is 96. 96 plus 16 is 112, plus 4 is 116, plus 1 is 117. So we clearly see that if we multiply the same numbers in binary, we get the same result, which is 117, and in this case we get the binary representation of 117, which is 110101. While there you see that multiplying numbers in base 10 and base 2 is exactly the same, and we also get the same result. So the important take home points here are, we define the term a multiplicand, which is this number. We define a multiplier, which is this number. Then the final result is a product, and each of these blue rectangles is a partial sum. So what did we do? We started from the LSB, least significant bit of the multiplier. We kept going left. If any of these bits is 1, we write the value of the multiplicand. If it's 0, we write 0. Then we move to the next bit of the multiplier, and essentially at every point we shift the partial sum one place to the left. So let's now have two quick definitions. A partial sum, it is equal to the value of the multiplicand left shifted by a certain number of bits, as we just saw, or it is equal to 0, right? And a partial product is essentially a sum of a set of partial sums. And the product is definitely sum of all the partial sums. But a partial product is a sum of a set of partial sums. Alright. We also know that if the multiplier has m bits and the multiplicand has n bits, the maximum size of the product will be, so in m bits, let's see. With m bits, assuming that it's an unsigned number, uh, the largest number that we can represent is 2 to the power m minus 1. Similarly, the largest number that we can represent with n bits is 2 raised to the power n minus 1, which is strictly less than 2 raised to the power m plus n. So the product requires m plus n bits. So now let's look at multiplying two 32-bit numbers. So let us first design a simple multiplier called an iterative multiplier that will multiply two 32-bit signed values. So this is the most general case. So multiplying unsigned numbers is always easy. But let's deliberately complicate our life and look at two 32-bit signed values. Let me just erase that. So we need two 32-bit signed values and we'll produce a 64-bit result. So what did we prove before? Well, we proved before that multiplying two signed 32-bit numbers and saving the result as a 32-bit number is the same as multiplying two unsigned 32-bit numbers assuming no overflows, right? So what we have essentially proven in chapter 2 is that, so if you can go back to chapter 2, but what we proved this result that if there are no overflows, then we can very well see, and let's say we want to multiply two signed 32-bit numbers, which can be positive or negative. Then what we do is that we take their 2's complement representations. So basically, if a number is u, its 2's complement representation is fu, right? So basically, let's consider an example. Consider a 4-bit system. So if a number is minus 3, then essentially f of minus 3 is plus 13, which is 1101. And if the number is plus 3, then the representation of plus 3, f of plus 3 is 0011. So what we have essentially proven is that to multiply two numbers and the representation in 2's complement of a product of two numbers is essentially the same as consider each of the numbers individually, take their 2's complements and then multiply them assuming that they are regular unsigned 32-bit numbers, you'll be just fine as long as there are no overflows. We, however, did not prove any result regarding saving the result as a 64-bit number, but this is what we know. So what we know is that if we want to multiply 2 times minus 3, so let's say in a 4-bit number system, we want to multiply 2 times minus 3. What we know is that multiplying this is equivalent to multiplying f of 2 times f of minus 3. So f of 2 is 0010. That's being multiplied with 1101. So actually if we multiply 2 times 13 we get 26, and since we can't save, but 26 we'll discard the highest bit because it's the 5th bit. So we'll be left with 26 minus 16, which is 10. So we'll essentially get 1010. 1010 is f of minus 6. So we thus see that treating these numbers as unsigned numbers and multiplying them is good enough. But in this case, this is only if the size of the result is also 32 bits. However, in this case, we are considering the possibility of saving the result as a 64-bit number, and we have not proven any theorems or any axioms or any lemmas for what should be done in this case. So let's take a look at a very important theorem that we need to prove. Once we are able to do that, we will find that a lot of the multiplication work that we do will become very easy to understand. So it's very important we take a look at this. So let us consider a signed n-bit number A. So let's first consider a number which is made by the first n minus 1 bits. So what we want to say is that the number A is equal to the number made by the first n minus 1 bits minus the MSB multiplied with 2 to the power n minus 1. So here AI is the ith bit in A's 2's complement based binary representation, where the first bit is LSB, and A1 to n minus 1 is a binary number containing the first n minus 1 digits of A's binary 2's complement representation. That's a lot of text. Let's consider an example, it will become crystal clear. So let's consider 3, and let's consider a 4-bit representation. This is 0011. This is exactly the same as we consider a number made with the first n minus 1 bits. So this 011 is still 3 minus the MSB is 0 times 2 to the power 4 minus 1. So but 0 times any number is 0, so basically this is equal to 3. So for a positive number, proving this is trivial, but the important case is a negative number. So let's consider minus 3. So minus 3's representation in a 2's complement system is 1101, right? So basically this is equal to, let's consider this number. So 101 is 5 minus the MSB is 1. So it's 1 times 2 to the power 4 minus 1. 2 raised to the power 4 minus 1 is 2 cube 8. So this is same as 5 minus 8. Right? So this is the important result that we need to prove, that if we consider, let's consider one more example. So let me delete this part and let's consider one more example. And here is what we need to prove. So let me consider, let me consider, let's say, the number minus 5. In a 4-bit representation, the number of minus 5 will be represented as plus 11, which is 1011. 1011 can be interpreted in another way. So this is 011, this is 3. So we are saying that minus 5 is equal to 011, 3 minus 1 times 2 to the power 4 minus 1, which is actually the case, 3 minus 8, which is minus 5, right? So in a sense, what we want to prove, which is this result, that given a signed n-bit number A, if we consider the number made by its first n minus 1 bits, right, if that number is A1 to n minus 1, and we subtract the MSB times 2 to the power n minus 1, we'll get the original number A. That's what we need to prove. So what we have seen is that for positive numbers, this is trivially true, because for positive numbers, the MSB is 0. So since the positive number is 0, we put 0 here, and 0 times any number is 0. So essentially this part goes away, right? So in any in any positive 2's complement number, the MSB is 0. So naturally, if we get rid of the MSB, the number that is left will be equal to the number itself, right? So here we are assuming that this number is unsigned, so it will be equal to the number itself. But the important point that we need to prove is that for negative numbers, this result holds, right? That if I take any negative number, again consider one more example, minus 4. Minus 4 is 1010. Minus 4 is also equal to this. Let's take 010, which is 2, minus 1 times 2 to the power 4 minus 1. Oh, oops, sorry. I made a mistake in that. I'll just go once again. So let's consider minus 4. So minus 4 is actually plus 12. So as per this theorem over here, A1 to n minus 1 is actually this number here, 100, which is plus 4. And so essentially minus 4 is equal to 4 minus 1 times, we are considering n as 4, a 4-bit number system, which is 4 minus 8. So the question is that why does this thing hold? We have already proven this in chapter 2, but we want to prove it once again because we'll really be using this result. We'll be heavily using this result in all our work on multiplication as well as division. So we sort of want to ensure that we understand this very, very well. So as I said, for positive numbers this is trivially true because an is 0. So basically if we just discard the MSP bit, the number remains the same and a is equal to the number made by the first n minus 1 bits. For negative numbers, the situation is slightly different. So let's consider a proof. Alright, so let's consider the number a to be less than 0. So if the number a is greater than 0, this is a trivial result. So if it's less than 0, let's also look at the representation of a. So let's consider the unsigned number that represents the 2's complement representation of a. For example, if a in a 4-bit system, if a is minus 3, then f of a is plus 13. If a is, let's say, minus 2, what will be f of a? It will be plus 14, so on and so forth. So what we can say is that this number f of a is essentially equal to the number which is formed by considering the first n minus 1 bits of the 2's complement representation of a plus 2 to the power n minus 1. The reason that I can write it this way is because for every negative number, the most significant bit is 1. It's 1. So basically, any number of this form will expand to 2 to the power n minus 1 plus something. So that's the reason, since the MSP is 1, I can write 2 to the power n minus 1 over here plus the number formed by the rest of the digits, which is rest of the bits, which is a1 to n minus 1. Similarly, I can write one more equation. So in this equation, what I can write, so this follows directly from the definition of the 2's complement, that f of a is equal to 2 to the power n plus a. So why is this the case? Let's just consider these examples to find out more. So when we want to find the 2's complement representation of minus 3, what we do is we actually add 16 to it, right? So when we add 16 to it, we get plus 13, which is its representation. Similarly, when we want to find the 2's complement representation of minus 2, we also add 16 to it in a 4-bit system to get plus 14. So essentially, if we want to find the 2's complement representation of any number of the form minus u, where u is positive, its representation is basically 2 to the power n minus u, right? So basically, in this case, since the number is negative, we just add it to 2 to the power n. And so for example, I want to find the representation for minus 1. I just add it to plus 16, so it is plus 15, which is 1111. So given these two equations, given equations 1 and 2, what is it that we can write? We can write and since we know that the MSB bit is 1 for a negative number, we can multiply this with an, when an is the nth bit or it's the MSB. So this expression over here, a is equal to the number formed by considering the first n minus 1 bits in a's 2's complement representation, which is this number over here, minus 2 to the power n minus 1 times an, where an is the nth bit, and in this case we know it's 1. So we proved it for the case that a is less than 0, and the proof for the case that a is greater than 0 is trivial. The main reason being that an is 0, and so we remove 0 out of the number, we have the same number. Alright, so given the fact that we are armed with this proof, let us move forward and let's try to design a multiplier. So let me just make one more point before we proceed. I just want to repeat it because it's very important. So let me go to this slide. So what we proved in chapter 2 was something like this, that when we multiply two signed 32-bit numbers and save the result again as a 32-bit number without any overflows, it is exactly the same as considering the unsigned representations. Considering that not the unsigned representations, but considering both the 32-bit numbers to be unsigned numbers and performing regular unsigned multiplication on them, and then using the last 32 bits as the result, right? So that's what we proved, and we showed examples that it works, and we also theoretically proved that this result is correct. In this case, what we want to do is slightly more generic and more complicated. We want to multiply two 32-bit numbers, no doubt, right? So we want to multiply, let's say, numbers a times b where there are 32 bits, and we want to save it in a number called c. But this number is, mind you, not a 32-bit number, it's a 64-bit number. It's a larger number. So this result will not hold, but we'll find that with the help of this theorem over here, we will be able to solve this problem very easily. So let's now take a look at the iterative multiplier. So the iterative multiplier is a very simple structure, as can be seen. So we have the multiplicand, and the multiplicand is stored in a register. So let's call the register n. Then we have the multiplier, so we'll be referring to the multiplier as m. So the aim is to compute the product, which is m times n. So in this particular scheme, we have two registers that we shall use. So we are doing, mind you, 32-bit multiplication. Register U is a 33-bit register. So this is 33 bits. And register V is 32 bits. So why is this 33? Well, we have an extra bit to take care of overflows. That's the only reason. Otherwise, there's no other reason. So basically, both these registers act as the same as a single register for the purpose of shifting. What this means is that I can shift both the registers to the right. So then the least significant bit of U will become the most significant bit of V. Similarly, I can shift both the registers to the left. Then the most significant bit of V will become the LSB of U. So for the purpose of shifting, they act like a single register. So when we shall start the algorithm, what we will do is that we'll load the multiplicand into the register n, and we will load the multiplier into V. So we will start with having the multiplier. And register U will contain all zeros. Alright, so that is the way that we start. We load the multiplier in register V. Register U will contain all zeros. And the multiplicand will be in register N, which is shown on top. And we'll have a circuit over here where we'll load the current contents of U. We'll add it to the multiplicand. And the result of the addition will be fed back to the register U. So that's pretty much the only circuit, but let's take a look at the algorithm that will show how exactly this circuit works. So the algorithm is as follows. So we want to multiply two 32-bit numbers and produce a 64-bit result. So we start out with having a multiplier in V. So the multiplier is loaded in register V and U is 0 as shown. and the multiplicand is in register n. So essentially, to avoid overflows, we made U a 33-bit register. So the lower 64 bits of the UV register combined will contain the product at the end. So what we shall do is that we shall start a for loop that will iterate for 32 times. Standard way, we have a variable and we iterate for 32 times. So essentially at this point, I will go from 1 to 32, 32 times because there are 32 bits. So let's consider the first iteration. If the LSB, the least significant bit of V, which contains the multiplier, is 1, which basically means we come here and we take a look at the least significant bit. If this bit is 1, so what is it that we need to do? Well, what we need to do is that we need to add the multiplicand to the accumulating partial product. So since the first iteration, the partial product will just be the multiplicand itself. So clearly in the first iteration I is 1. This is less than 32. So what we do is we add u. So we set u to u plus n. So u initially is 0. So essentially what we do is that we set u to n. So that's anyway the first thing that we should do. That if we see that the least significant bit of the multiplier is 1, then what we should do is that we should essentially the product will be the multiplicand itself. So we set u to u plus n. And so let's not talk about this part right now. We'll talk about it later. And then what we do is that we take the register uv and we shift it to the right. One arithmetic right shift to preserve the sign bit. We shift it to the right by 1 position. So let's see what's happening. So initially we have the register U and the register V, and the register V contains the multiplicand. After that, let's say that this bit is 1. If this bit is 1, then the multiplicand the multiplicand occupies register U, and register V will contain the multiplier M. So then we shift it to the right. If we shift it to the right by 1 position, then this is still register U and register V. So if I do it, then what will happen is that the product will sort of be in U and as well as in 1 bit in V. So this will sort of be the partial product, right? The partial product will span both the registers, and the least significant bit of the multiplier will fall out from the right. So this part will contain the multiplier, and the multiplier initially at 32 bits, we'll only have 31 bits of the multiplier left because we shifted it to the right by 1 position. So then again we'll come to the next iteration, again take a look at the least significant bit of the multiplier. If it is 1, we'll again add it to the partial product. If not, we'll say if the least significant bit of V is not 1, then we don't need to add anything, because if we go back to this example, so what we are essentially doing is first we are considering this bit. So this is 1, so essentially we set u to the multiplicand. Then we shift both the multiplicand and the multiplier by 1 position. So this bit falls off from the right. So then we consider this bit. Since this bit is 0, we don't have to do anything. We again shift 1 step right. So this bit becomes the least significant bit. And since this is 0 also, we don't do anything till we come to the last position. We'll not discuss what we do in the case of the last position because this varies for signed and unsigned operands. So but the important point to note from this particular diagram is that if the bit under consideration in the multiplicand is 0, then we don't do anything. So in a sense, we don't update the partial product. So let me once again explain what is the partial product. So a partial product is a sum of partial sums. So what we essentially do in a multiplication is that we first create the partial sums. So the second partial sum, which is 0, 0, 0, is written in such a way that it is left shifted by one place as compared to the previous partial sum. So essentially the ith partial sum is shifted to the left by one position as compared to the I minus 1th partial sum. So if we consider the first I partial sums, we can add them up to make a partial product. So then the partial product will be added to the partial sum to the next partial sum. So let's come back to the algorithm. In the algorithm, we run the loop for 32 times. For the first 31 times, this is what we do. We take a look at the least significant bit of V. If it is 0, we don't do anything. We don't have to do anything because in this case, the partial sum is 0. However, if it is 1, we add it to the register U and we proceed. At the end of this if statement, we shift the UV combine one step to the right using an arithmetic right shift operation because we want to preserve the sign. Now the first thing that needs to be explained is that why do we shift one step to the right? So let's look at a general case. Let's look at some iteration in the middle. Let's say the ith iteration where I is clearly not 32. So in the ith iteration, so in iteration number I, let's consider this point, exactly at this point. So here we have already computed the partial product for the first I partial sums. So the partial product is contained partly in register V also. So maybe we can say that this entire region contains the partial product, which is the sum of the I first I partial sums. And the remaining region contains the bits of the multiplier. Then what we do is that we shift the UV register combine one step to the right. So effectively what this means is that we have one bit. So basically when we shift it to the right, we maintain the sign bit as well. So but disregarding that, the partial product is pretty much contained in this fashion. This is for register U, and again for register V, the partial product will again come here, and we will have the remaining set of multiplier bits where one bit just fell out because of the right shift operation. So what we do now is that we come to the next iteration. So in the next iteration, if the partial sum is 0, well and good, we don't have to do anything. But let's consider the case where the partial sum is 1. When the least significant bit is 1. So in this case, what we do is very interesting. So in this case, what we do is that we add the multiplicand to the register U. So the question is that why do we add the multiplicand to the register U? And again, after adding, the result of the addition is used to update the register U. So essentially, we add n plus u. So we have an adder like this, we add n plus u, and the result of the addition is fed back to register U. So this is pretty much the same as, so what we are doing, if I just take it out, it is pretty much the same as doing the following addition, where I write register n here, which is the multiplicand, and then I consider the partial sum, where the partial sum is starting one bit to the right. So basically, if you think about it, so this is pretty much where the partial product is ending, and the partial sum has one extra bit. So I'm just reproducing the same thing, but I'm just writing it in a reverse fashion. If I write it if I write it this way, the multiplicand is one step to the left, But if I see from the point of view of the multiplicand, the partial product is shifted one step to the right. So essentially the partial product will be a number of this fashion. And then we perform the addition. So after performing the addition, we get a new partial product, which adds the multiplicand as well. Subsequently, what we do is we come to this step and we again shift it one step to the right, and again we add the multiplicand. So why we are doing this will be very self-evident if we take a look at this figure once again. So let's consider the last step. So in the last step, so here mind you we are multiplying unsigned numbers, and in our algorithm we are multiplying signed numbers. So there's a little bit of a difference, but let's still take the unsigned example. So in the last step what we are doing is that we are writing the multiplicand, which is n, and we are adding it to the partial sum, right? So basically the, as far as we are concerned, the multiplicand is essentially shifted one bit to the left as compared to the previous partial sum. So we essentially, this is exactly the same as we take the partial sum. We take the first I minus 1 partial sums and we shift that one step to the right as compared to the last partial sum. So the effect is the same. You shift one number to the left and then add, or you keep one number constant and you shift the others to the right. The relative movement is the same. So in the case of a regular multiplication, we just write the partial sums and we keep on shifting them one place to the left. Another idea can be that, for example, we take the partial sum as 1101 first, and we shift 1101 one step to the right, and then we add 0000. Then we shift it one step to the right, and then we again add 0000. Then we again shift this one step to the right, and then we again add, which is exactly what we are doing. So instead of shifting the partial sums one step to the left here, what we can do is that we can shift the partial product, which is our current accumulated set of partial sums, one step to the right, and of course not lose any bits, and keep on adding the multiplicand if need be. So the effect is the same. Essentially shifting a number left and shifting a number right depends on from where we are looking at it. So what we are essentially doing in this line over here is that the current computed partial product is being shifted one step to the right, and then we are adding, if the current LSB is 1, we are adding the multiplicand. So the effect is the same. The effect is basically that after shifting this, after shifting the partial product k steps to the right, we are essentially multiplying the multiplicand by n to the power k, which is fine. That's exactly what we wanted to do. So let's consider the partial sums in a regular multiplication. So if we consider the kth partial sum, right? So let's consider the kth partial sum. So essentially this partial sum is either 0 or it is the multiplicand multiplied with 2 to the power k, because it is shifted k places to the left. So here what we are doing is that we are essentially doing the same, but we are just keep changing the baselines and we are moving it to the right. So it will appear that the multiplicand is first being displaced by k steps, then by k plus 1 and k plus 2 and so on, because this boundary over here is moving to the right. So the multiplicand over here will first appear to be left shifted by k steps. In the subsequent step, once this boundary moves one step to the right, from this point the new multiplicand will look like shifted by k plus 1 steps to the left, and so on. So basically the crux of the issue is that instead of shifting the partial sums which contain the multiplicand 1111 steps to the left, it is a better idea in this scheme to keep the multiplicand where it is but shift the accumulating partial product to the right. So it's the same thing. Mathematically, it's the same thing. It's just that it's easier to implement in hardware. So let us now consider the last iteration. So the last iteration will pretty much bring us over here. The last iteration is somewhat special. So the reason being that this is a signed number, and so we are the multiplicand on top and a multiplier at the bottom. So when we reach the last iteration, which is the 32nd iteration, if the LSB is 0, we don't do anything, which is fine. But if the LSB of V is 1, so LSB of V basically means that in the last iteration, if I consider the register pair U and V, then only the last one bit of the multiplier will be left, which will be its MSB. So the multiplier is negative, then the MSB will be 1. So in this case, what we are suggesting is that we don't follow this part of the if loop, if statement, but we come here and instead of adding the multiplicand to the partial product, we subtract the multiplicand from the partial product. That's all that we do. And we do one more shift and we are done. So the question is, why are we doing it? So the reason that we are doing it, we have to go back to this theorem over here, which essentially tells us that the number is, so if I consider its 2's complement representation, it is the same as an unsigned number that is formed by the first n minus 1 bits, and from this we subtract an, which is the MSB, times 2 to the power n minus 1. So since the MSB is 1, so basically A is equal to, when A is negative, so when A is negative, A is equal to so assume that A is the multiplier and we are trying to multiply B times A, where B is the multiplicand. So then what we will have is that we'll have B times which will happen in the first n minus 1 iterations. Then we need to subtract B times 2 to the power n minus 1. So which is a left shifted version of B, and B is the multiplicand over here, and that is exactly what we are doing here. So we are subtracting the multiplicand from U, and since in the last iteration we have reached here, so effectively our so you can think of it that our base our least significant bits position is over here. So from here, if I look at the multiplicand, which is over here, then it appears to me that the multiplicand is left shifted by n minus 1 places, right? And so what I am doing is, in effect, I am left shifting the multiplicand by n minus 1 places, and I am subtracting it from the accumulated partial product, which is this value. So this justifies this step, that if the multiplier is negative, then in the last iteration, instead of adding the multiplicand, instead of adding n to the partial product, which is essentially I am adding it to register U, what I do is I subtract. This is a very important thing, should be kept in mind, and a lot of times students actually make mistakes. But the important point is that this has to be kept in mind, that in this multiplication operation, in the last iteration, instead of adding the multiplicand to U, to register U, we subtract it. So let's consider an example. Nothing is clear without an example, so it has to be considered. And let's see. So let us assume that the multiplicand is the number 2, 0, 0, 1, 0. The multiplier m is the number 3, which is 0, 0, 1, 1, and we have a 4-bit number system. At the beginning, the register V contains the multiplier, which is 0, 0, 1, 1, and U contains 4 plus 1, 5 zeros, just to take care of overflows. So let us consider 2 points, which is before the shift. Let me call it before the shift, And let's consider one more point, which is after the shift. So before the shift, we will have, so we'll consider the LSB of the multiplier. So the LSB is 1. So we will add the multiplicand to register U, we'll add 2. So before the shift, we'll have 0, 0, 0, 1, 0 because the multiplicand is added. And we'll have the multiplier, which is 0, 0, 1, 1, which was already loaded at the beginning. Then we will do a right shift. So right shift means that this bit will come here and this bit will come here and this bit will essentially fall off. Then let's come to the next iteration. So what is the least significant bit of V? It is 1. So if it is 1, what we will do is that again we'll add 2, which is the multiplicand. So 1 was there, we'll add 1 0 plus 1 to make it 1 1. The rest remains the same. And subsequently we shift. So this bit will come here, this bit will come here, and 1 will fall off. The rest of the bits of the multiplier are 0 0, so we will nothing will happen before the shift, but we will after the shift the bits will each move by 1 position, and then the same happens in the fourth iteration where the bits move by 1 more position. So at the end of 4 iterations, because it's a 4-bit number system, the computation is done. The product P is 0 1 1 0, which is 6, which is exactly what we would expect. 2 times 3 is 6. So this is exactly what we would expect. And how is this happening? We are considering each bit of the multiplier, and based on that we are either adding the multiplicand to the partial product, or we are doing nothing if the bit is 0. Let us now consider the more complicated example where the multiplier is negative. This is where a lot of our understanding will be tested. So let's look at it in some more detail. So we first load 3 into register N, which is the multiplicand. So this is 0 0 1 1, and we load minus 2 into register M, which is also loaded into register V. And minus 2 in a 4-bit number system is plus 14, which is 1 1 1 0. Then we start. So the first thing that we do is that we take a look at the LSB of V. So LSB of V is 0, so we don't do anything. So before the shift, we'll have U as all zeros and V as 1 1 1 0, and then we shift. So each of these bits get shifted one step to the right. Subsequently, we find the LSB of V to be 1. So we add 3 to U. So we add 3. So we have 0 1 1 over here, and we have the existing multiplier over here. We do one right shift, so all the bits move one step to the right, and then they remain there. After that, we take a look at the LSB of V once again. It's again 1. So we again add 3 to register U. So 3 plus 1 is 4. So this becomes 1 0 0 and 1 0 1 1. And we do a right shift. So all the bits again move one step to the right, and 1 falls off. Finally, we go to the fourth iteration, which is the fun part. And here we find that the least significant bit of V is 1. And this is the last iteration, right? It's a 4-bit number system and it's the last iteration. Since it's the last iteration, instead of adding the multiplicand, we'll subtract the multiplicand. So basically, what was the number we had before? We had plus 2. Now we subtract 3 from 2. So then the result is minus 1, and minus 1 is 1 1 1 1 1. So this is what we get before the shift, and after the shift we essentially 1 will fall off. This one comes here, this one comes here, the rest of the numbers get shifted, and we have a sign extension. So if we take a look at the product is basically 2 plus 8, 10, and in the 4-bit number system 10 is the same as minus 6. Did we expect that? Of course we did. 3 times minus 2 is equal to minus 6. So there you go. Lo and behold, it works. And it works, fantastically well. So here the trick here was that in the last iteration, which was the fourth iteration, instead of adding the multiplicand, we actually subtracted the multiplicand. And the reason we did this is because of the following theorem, which basically said that look, you treat uh, a number. So let's assume that, let's go with more conventional terminology. So we are multiplicand is being multiplied with the multiplier. So this can be written as, so the multiplier, let's consider the first 1 to n minus 1 bit. So that is one unsigned number. And if the number is negative, then the MSB is 1. So essentially in the first n minus 1 iterations, we multiply the multiplicand with the first n minus 1 bits of the multiplier. So this is the partial product at this particular stage. After that, we need to subtract it with the multiplier shifted in a small n minus, so there's a capital N which is the multiplicand, and then there is a small n which is the number of bits in the number system. So we want to make this distinction. So it's not the multiplier shifted, the multiplicand shifted by small n minus 1 steps, right? So that is essentially what we want to ensure in the last iteration. So from the partial product, we need to subtract the multiplicand shifted by n minus 1 steps, which basically means that you take the partial product and you sort of you shift it n minus 1 steps, and then you keep the multiplicand as it is, and then you add it. So we have been looking at different versions of the same idea, but the main reason that we do a right shift is basically to create a relative movement between the multiplicand and the partial product. So always the multiplicand should appear, the next partial sum should appear one bit left shifted as compared to the previous partial sum. And the way that this is ensured is basically by having a combined register, and initially the partial product is only in U and the end of the partial product is over here. So we keep on moving the end by one place. So if we keep on moving the end, if we start looking at the multiplicand from the end of the partial product, it will appear shifted to the left by increasingly one position, which is exactly what we wanted to achieve. So after seeing these examples, let's textually summarize the algorithm. So we take a look at the LSB of V. If it is 0, we do nothing at all. If it is 1, we add the multiplicand to U. And right shifting the partial product is the same as left shifting the multiplicand, which is done in every step except the last step, which is different. In the last step, if the MSB of the multiplier is 0, which means the multiplier is positive, we do nothing. If it is 1, means the multiplier is negative, so we use this relation over here, and this number is equal to 1, which is the MSB of the multiplier. So we basically subtract the multiplicand if the MSB of the multiplier is 1 from register U. So what is the time complexity? So the time complexity is there are n loops. So that will take order n times the time of each loop. And each loop, what does it have? It has an addition or a subtraction. So an addition or a subtraction takes log n time, as we have seen from our previous discussion. We can use a carry lookahead adder. So the total time that is required is order n times log n, which is order of n log n. So given the fact that we have seen this iterative multiplier, can we make it a little bit faster, right? Maybe if not asymptotically faster, at least faster in practice. So well, it turns out that we can make our iterative multiplier faster. So if there is a continuous, so let's understand, if there is a continuous sequence of zeros in the multiplier, we do nothing, right? Which is good, which is very good for us, that we do nothing at all. So there is no addition or multiplication involved. However, if there is a continuous sequence of ones, then in the iterative multiplier we keep on doing additions and a subtraction at the end. Maybe we can do something smart. So that's where, when idea strikes us, right? So what's the idea? So let's take a look at this simple identity over here. So let's consider this. Let's consider the sum of the powers of 2 to the power k from k equals I to k equals j, where j is greater than I. So in this case, if I just do a simple GP summation, it will turn out that this is equal to 2 raised to the power j plus 1 minus 2 raised to the power I. So this is a simple summation that you can do. So it's 2 raised to the power j plus 1 minus 2 raised to the power I. So that this means that for a sequence of ones from that are from position I to j, uh, we typically perform j minus 1 additions, and so basically we this is what we do, that we just keep on performing additions, right? So let's do a new method. So the new method is called a Booth multiplication method. So let's say that when we scan bit I, so basically let's take a look at this. So let's assume we have a sequence of ones from bit position I to j in the multiplier. So in the multiplier we have a sequence of ones. So when we scan bit position I, so assume that before that we have a sequence of zeros. So in an island of zeros, we suddenly have a sequence of ones from I to j. So when we scan bit position I, let us subtract the multiplicand from u, right? And uh, let us keep then shifting the partial product as we do. And when we scan bit position j plus 1, right after j, when we again see that there is a transition from 1 to 0, let us add the multiplicand when we scan bit j plus 1. So since we right shift the partial product at every stage, in effect what it does is that it effectively adds 2 raised to the power j plus 1, because if you remember our previous discussion, we had said that the partial product occupies the register u entirely and a part of register v, and in every iteration the LSB of the partial product keeps moving one place to the right. So if we start looking from the LSB towards the multiplicand, it will look like it is moving one step to the left. So basically in the ith iteration, since we are subtracting the multiplicand, we are subtracting n raised to the power 2 to the power I. And in the j plus 1th iteration, since we are adding the multiplicand, it looks like we are adding 2 to the power j plus 1 times n. So in effect, we are adding this number to the partial product. Well, this is exactly what we wanted to do. I mean, in this case, when we have a continuous sequence of ones from I to j, what we are adding to the partial product is essentially a summation of 2 raised to the power I till 2 raised to the power j multiplied by the multiplicand, which is the multiplicand times. So the summation of this, as we have seen, is 2 raised to the power j plus 1 minus 2 raised to the power I. So this is exactly what we wanted to do. So the insight is that if we have, let's say, a string of ones, and there's a 0 at the beginning and a 0 at the end, so basically this is what we are trying to say, that even if, let's say, we are looking at the first bit position and the first bit position is a 1, we'll assume that just before it there is a hypothetical 0. So this is what this line means. So the moment we see a 1 and we see a continuous run of ones between position, let's say, I and position j, and it also says that the count starts from 0, which means that if it's the first position, then we'll have 2 raised to the power 0, but that's okay between positions j and I. In effect, To the partial sum, we are adding n times. At this point it is left shifted by I positions and then plus j positions. With a little bit of algebra, this is what we get, which is the same as subtracting it once and adding it once more. Subtracting it once at the ith position and adding the multiplicand once more at the j plus 1th position to the register u. So the operation of this algorithm is fairly simple. Let us consider bit pairs in the multiplier, a current bit and previous bit pair. And we take actions based on the bit pair. So we have an action table, current value and previous value. So if the current bit is 0 and the previous bit is 0, well, nothing needs to be done. We are in a run of zeros, so absolutely nothing needs to be done. If the current bit is 1 and the previous bit is 0, means a run of ones is starting. So as discussed on the previous slide, we subtract the multiplicand from u. Then if you are in the middle of a run of ones, so current bit is 0, current bit is 1, previous bit is 1, we don't do anything. And again, when there is a transition from a 1 to a 0, then we add the multiplicand to u. So in effect, what we are doing is that we are adding this quantity to u, which would have been the same as j minus I plus 1 repeated additions. Instead of doing this, so we are essentially using this identity over here, which is saying that instead of doing j minus 1 repeated additions, you can subtract once and add once. As simple as that. So that will save us some work. Asymptotically, no, because in the worst case, you can always have a multiplier that is of the form 0, 1, 0, 1, 0, 1, 0, 1. But in most cases, if there is a continuous run of zeros or a continuous run of ones, we can really save a lot of effort. So let us take a look at the Booth's algorithm, which uses exactly the same hardware plus a little bit of extra circuitry, but the hardware is the same as the iterative algorithm. So we multiply two 32-bit numbers to produce a 64-bit result. The multiplier is in V and U contains a 0. The multiplicand is in N and the lowest bits of 64 bits of UV will contain the result. So let us do the same thing. Let us set I to 0 and let us iterate for 32 times, each time increasing I. Let's start with by considering, as mentioned before, the previous bit to be 0 and let the current bit be the LSB of V, right? The current bit that we are considering of the multiplier. So let's take a look at the tuple of the current bit and previous bit. So if a run of ones is just starting, in the multiplier 0, 0 and 1. So we are making a transition from 0 to 1. This is the time to do a subtraction. U is U minus N. Similarly, if a run of ones is just ending, so you have a run of ones over here and this is just ending, then what we do, right? From 1 we are moving to 0, current bit is 0, previous bit is 1. So as discussed before, we add the multiplicand to u. So in the first case we will subtract when a run of 1 is beginning, and in the second case we'll add. Then we need to set the previous bit to the current bit and then perform a right shift as was done before and keep going on. So let's try to outline a proof, but again the proof is complicated. So I'll not go into the details of the proof, and the readers are expected that if you want to know more about the proof, which is anyway star marked inside the book, so you should take a look at the proof inside the book. So the proof is difficult, but I'll tell you what makes the proof difficult. The fact that makes the proof difficult is like this, that let's assume that the multiplier is a number of the form 1, 1, 1, 0, right? So after that, we can have any combination of bits, it does not matter. So which means the multiplier is essentially negative. So when we come at this point, we are making a transition from 0 to 1. So we subtract the multiplicand, which is this line over here. And then we just keep going. We just keep going on and on and on, Finally, we reach the last bit, and so the uh, runner once is continuing, so we don't get a chance to actually perform this addition, and then we finish. So we need to say that for signed 2's complement numbers, this is absolutely fine in the sense that we can do a subtraction over here and essentially never do the addition. That's exactly what's happening. If we have a runner once and the runner once continues till the most significant bit, then we'll do a subtraction, but we'll never get the opportunity to actually do an addition. And we need to say in a 2's complement world, this is fine. So this requires a little bit of algebra and it's somewhat difficult, but we shall see examples of this working. So let me explain the insight once again. I'll give a brief overview of the proofs, but I'll be very, very brief because the proofs are complicated and an online lecture is probably not the best place to discuss the proofs of the Booth's algorithm. But we'll discuss the examples though. So the main insight is this. Well, look, in a multiplier, if we have zeros, we don't do anything. So that's the best uh, thing for us, that if a number is zero, it essentially saves us effort. But if a number is 1 in the iterative multiplier, we are either doing an addition or a subtraction, which used to take effort, it used to take log n time. So since this was taking effort, we said what happens if we have several consecutive ones. So let's say we have, k consecutive ones separated by zeros, right? Then in the case of an iterative multiplier, we are essentially doing k additions, which was a lot of work. What we are saying is that it's not required. What we can instead do is that we can do one subtraction at this point and one addition at this point that is equivalent to actually doing k additions, because it's a simple sum of a geometric series. So instead of adding k numbers, we can essentially do one subtraction and one addition and we are done. So that's the reason we look at transitions from 0 to 1 and 1 to 0, and if the transitions are fine, if the transitions are there, then there is nothing much that we need to do. We just need to work on whenever the transitions are there. In a 0 to 1 transition, we need to subtract the multiplicand. In a 1 to 0 transition, we need to add the multiplicand. That is pretty much the only thing that we need to do. But proving it for 2's complement signed numbers is a different issue altogether. So let me give a very, very quick overview. So assume that a multiplier m is positive. If the multiplier m is positive, then so the way the proof works is that we try to match the state between the iterative algorithm and the Booth's algorithm, and we shall see that since at the end, things the MSB is 0, so all the runs of ones are in a sense taken care of because we do a subtraction and then we do an addition. So the main problem comes when we have negative multipliers and then we further divide it into two subcases. When the MSB bits of the multiplier are 1, 0 and when they are 1, 1. And so I'll not discuss these because this is fairly complicated, and but the main idea is that it is possible to prove that in the case the Booth's algorithm works correctly when the multiplier is negative, as represented in a 2's complement fashion. But how it's done, it's better to take a look at the book, and even in the book the proof is fairly long, a couple of pages if I remember correctly. So let me skip that, but let's take a look at the example, which is a nice and fun part. So in the example, so let us multiply 3 with 2. So the multiplicand n is 3, 0, 0, 0, 1, 1. And the multiplier is 2, 0, 0, 1, 0. So let's again consider 2 points before the shift and after the shift. So the initial previous bit is 0. So basically the state that we see here is the LSB of V is 0 and the previous bit is 0. So the current bit previous bit pair is 0, 0. So essentially we don't do anything but we shift. So the 1 will come over here. That's all. Subsequently what we do is that we look at the current bit previous bit pair, which in this case is 1 0. So we see a 0 to 1 transition. So in this case, what we do is we essentially subtract the multiplicand, which means that we add -3. And -3 would be this in a 5-bit representation. Why? Because you just add +3 to it. So you'll clearly see that the result becomes 0. And so this is what -3 is. So basically we can also see for a 4-bit -3 will be 1101, and we are just extending its sign, right? So this is -3. And subsequently we do a shift and we maintain the sign bit. So we perform an arithmetic right shift. So the 1 gets thrown out and the rest of the bits get shifted by 1 position to the right. Exactly the same as the iterative algorithm, and this is the sign extended bit. Now the least significant bit is 0 and the previous bit is 1. So there is basically again a transition from 1 to 0. So in this case we add 3, right? We add 3. So if we add 3, then we are adding 0 0 1 1. 1 plus 0 is 1. Then when we add 1 to these string of 4 ones, we'll get 4 zeros. And the rest remains the same. So then we do a right shift. So the current bit and the previous bit are now 0 0, so nothing needs to be done. We do one more right shift, and the product that we end up with is 0 1 1 0. 0 1 1 0 is 6, and this is exactly 2 times 3. So this is exactly what we wanted. So 2 times 3 is 6, and this algorithm is faster. The reason this algorithm, well, so one thing is we didn't see a run of 1, so we are not able to see the power of it. But had there been a run of 1s, we would have definitely seen this algorithm, the Booth's algorithm to be faster. So let us now consider multiplier with a run of 1s. And also the multiplier is negative, so this represents a fairly complicated case for us. So let's start the way that we should start by first loading the multiplier into V. So the multiplier is -2 in this case, so it is 1110. We load all zeros into U, and before the shift we have U as 0000 and V as 1110. The reason being that the previous bit and current bit pair is 00. So since it is 00, we don't do anything. We don't do anything at all. So we just do a right shift. So all the numbers here get shifted to the right by 1 position. Subsequently, we need to take a look at the least significant bit of V, which is the current bit 1, and the previous bit is 0. So our current bit previous bit pair is 1 0, which means that there is a transition from 0 to 1. So given a transition, what we need to do is that we need to subtract the multiplicand, in this case add -3. So adding -3 to 0000 would be the representation of -3 in a 5-bit system, which is 111101. Why is this the case? Because this is, so in a 5-bit system, -3 will be actually plus 29. So this is 1, plus 4 is 5, plus 8 is 13, plus 16 is 29. And once after doing this, after the shift, we just shift it. So this 1 falls off to the right. We have all the numbers shifted to the right by 1 position, and we extend the sign. So the sign bit is 1, so we just extend it and we add a 1 over here. Now let us take a look at the current bit and previous bit pair. So in this case it is 1 1. Since it is 1 1, nothing needs to be done. So this is exactly where we are saving work. So we just need to do a shift. So let's do a shift. This 1 will again fall off, and each number is shifted by 1 place to the right, and there is sign extension. Again, let us take a look at the LSB. The LSB is 1 and the previous bit is 1. So again the current pair of bits is 1 1, so nothing needs to be done. We just need to do a shift, one arithmetic right shift. So this is where we end up at. So the final product is, if you consider a 4-bit system, it's 1010, and 1010 is minus 6. And we consider a 8-bit system, it's basically 1010 extended, it's sign extended, which is still minus 6. Is minus 6 the correct answer that we expect? Of course, this is what we expect. 3 times minus 2 is minus 6. But let me tell you the advantage of using the Booth multiplier. So had it been an iterative multiplier, we would have performed 2 additions here and 1 subtraction. So the addition and subtraction take more or less the same amount of work. So essentially we would have performed the work of 3 additions because there are 3 ones. But the interesting thing or the greatness of the Booth's algorithm is that in this case, we took advantage of the run of ones and we just performed 1 addition. If we assume that the addition takes most of the time, so this algorithm is faster by a factor of 3, right? So it's 3x faster, which is great, which is fantastic. That is exactly the kind of speedups that are required in modern high performance adders. Also, the other thing that you need to note is that the 2's complement system got taken care of automatically, right? So in this case, the multiplier is negative, and so we didn't have to do anything special, and it's just the run of ones ended and we finished the algorithm. So we didn't have to do anything else, and the product was, all set for us minus 6. So the fact that nothing needs to be done is something that should be proved, and we have proven that in the book. And also those who have read the proof in the book can actually also read the last 5 slides. That will sort of help you refresh the knowledge of the proof. Otherwise, the proof is somewhat involved. But in any case, the important point is that a Booth's algorithm takes advantage of a run of ones and has the potential of significantly reducing the number of add and subtract operations. Well, what's the time complexity? Well, the worst case input is 1010, which means all the time there is a transition. So we'll have to do an add or subtract. So the time complexity per iteration still remains log n, because that's how much an add or subtract takes. And if there are n iterations, it is still n log n. So the worst case asymptotic time complexity remains the same. But in practice, we will always have numbers that have some runs of ones. So in practice, we'll definitely see some speed up. So this is pretty much where the asymptotic notation fails to show obvious benefits. In any case, the Booth's multiplier is popular. It's heavily used, and it's particularly heavily used in small embedded processors. So that's where the algorithm finds a lot of utility and a lot of use. So now let's look at substantially faster multipliers that can work in order log n square or order log n time. So these multipliers will find their use in very, very high performance implementation. So let's look at it next.